So while the universe consists of an infinite number of possibilities and beyond that, as well as an infinite number of universes, you know, there have been much of speculation of how many different types of possibilities we've been able to find. And so as far as galaxies go, I mean, in a search to always find something new, and of course, you know, there seems to be many possibilities that still, maybe even to this day, scientists haven't found yet. But here are 4 types of galaxies that we know of as of right now that, you know, if you're actually very interested in, you can learn a little bit more about. So there's 4 main classifications that I've been able to find, at least, and it's you have spiral galaxies, you have barred red spiral galaxies, you have ellipticals, and you have what is known as irregulars. Now, in this video, I'm going to try to explain the best I can what the differences are and maybe how many galaxies we can kind of get, like how common they are, basically, because it seems like there might be other ones, but this is just one of the easier ways to narrow it down for right now. So start with the easier ones. So basically you have like the difference between a spiral and a barred spiral galaxy is basically, they're basically not really that much different, but they do consist of like spiral arms, a spiral shape, kind of like our galaxy in the Andromeda Galaxy. You can definitely see how it kind of wavers like a hurricane. There's like a spiral swirl, and then it just moves. You know, there's it's got like a halo, a bulge, spiral arms. Maybe some other stuff. And I mean, one of the major reasons why it might actually be like this is it depends on its orbits too, the stars, of course, but it also might have something to do with like the black holes that you can find inside of them, if that is the case. It just really depends on what's causing the gravitational pulls, as well as the way it looks, rather. So the luminosity, the mass, the forces of acceleration, basically, I'd say have like kind of a good portion of it. And I'm sure there's other things too, but basically, I mean, our galaxy, it's been debatable, like really how, well, I mean, I guess you could say anything is debatable in science. There's no end to really how many possibilities you can find. There have been people that have speculated it's 100,000 light years in diameter. Mind you, 1 light year is 5.88 trillion miles. Or if you want to go like a parsec, it's like 3.26 or 3.27. I kind of forgot off the top of my head. But basically 19 trillion miles, basically, if you want to really go that route. So yeah, basically parsecs is what they would use to measure the distance. I think it's 3.27. It's pretty close though. So if it's that close, then you're talking, I mean, our galaxy could be like at least like maybe 1.9 million light years in diameter. It really, I mean, there's just so much about our galaxy we don't know, and there's so many things happening at once that we don't see. Like even like where you can go on a starry night and you see like all these stars at once, especially where there's like no light interference aside from the stars itself. You're talking basically like that's all like the nearby stars that are in our galaxy. And I mean, there's so many. There could be trillions, or well, maybe not trillions, but I mean, maybe at least 8 trillion or maybe more. I mean, it's like there's just so much we don't know, and yet there's so many things that, I mean, even as like technology gets better, and you know, we always underestimate, you know, especially like objects that are so far away and you're like zooming in with enhanced, you know, magnification. You're really looking at so many possibilities that it's possible that it gives off like the illusion of size based on the distance and length. So I mean, even a scientist might have formulas they use to figure certain things out, but there's always that optical difference. Like I'll give you an example so you kind of know what I'm saying. You know, like take for example when you look at the sun and the moon in the sky, when you see it, they kind of look like the same distance, they kind of look like the same size. But you'd be very surprised that there really is a huge difference. Obviously, the moon is closer to the Earth than the sun is, and so technically the further the sun is, but you can still see the sun. So that means that, and it's like the same thing with, I'll give you another example, like, you know, like Venus. You can barely see the planet, but it's closer to the Earth. But the sun is so much farther away, but you can see the sun visibly because of the illumination and the size of it. So that's really the only thing that can make a difference. So you've got these galaxies that they're so far away, and yet they're so huge that it's like, even for the distances that, you know, we attempt to try to rationalize where they're at, how far they are, and continuing to exceed away from each other because everything's moving in space. You're talking about how a lot of stars would actually be probably even bigger than what they originally are, because with the illumination as well as the mass, I mean, you know, you're talking about there's so many size differences that anybody can estimate. And it seems like, you know, the more you enhance something and the closer you zoom into it, the bigger it actually looks because you're seeing it up close. But with stars and all that, I mean, we can only really think, well, you know what, maybe they're actually bigger than what they seem based on the magnification process as well as the enhanced material. So it's actually very interesting, the ideas we came out with, but it does seem like, you know, objects have always been it's just that they're always greater than that, you know, whether it's a star or a galaxy or just a distance in space. It's really, really amazing how much a distance of measurement can cover in a different dimension itself. So basically a buried spiral galaxy basically has what it sounds like. It's got like a central disk somewhere in the middle, and it composes, basically our solar system itself is considered a buried spiral galaxy. Basically it affects like the halos, the disks, the spiral arms, basically the star dust and material that is made up of the galaxy. It affects like half the size, and it can affect kind of the illumination. It basically is just another way that the galaxy works, and therefore it kind of just affects, like, it's like a subclassification. It's not too much different, as said before, as a spiral galaxy, but basically it just kind of, some things can be found a little bit differently, maybe act a little differently, but it's still able to produce like the starry mass, dark matter, dark energy, radiation basically. And you basically have planets that, you know, can possibly support life, depending on how the illumination and stars are. But that's really getting more into like the star itself and its properties rather than just the whole galaxy. So it's actually really interesting. So like our galaxy is technically it's not a buried spiral galaxy, but it's more of it's just a spiral galaxy for the most part. It's pretty neutral when it comes to anything else. Like if you were to see pictures of the Milky Way galaxy, you can definitely see it being a spiral galaxy. It stands out because you got the blue nebulous gases and the light, I believe, is what really gives it off. So basically an elliptical galaxy is what is known as, it basically consists of old stars, and they're kind of deformed in a way. They're not necessarily like, it's like they didn't form like perfectly. I mean, then again, most spheres in the universe aren't. But in elliptical galaxy, you most likely will find like stars that are kind of shaped in like what is known as like elliptoids. So they're like kind of like squash stars basically, or spheres. They basically kind of give off like a weird, it's like maybe they're like there's a lot of like, I'd say like maybe pressure points and maybe certain elements that just have a different unbalanced nature that cause them to do what they do. So basically the pressure, the magnet fields, maybe the atmospheres are kind of thrown off a little bit, and therefore somewhere in the star cycle it can create like a runoff and a different type of star altogether. So its gravity might be different, its acceleration might be a little lacking, and there's like a curvature somewhere between where it's just not, it just kind of formed wrong, you know, if that makes sense. So basically it does certain things better than it should, and some things it performs under average, and therefore like certain stars will do some of the strangest things. Like kind of like, again, kind of going back to like, I'll give you an example, like Stephenson 218, for example, you know, one of the largest known stars that we know of. You know, they considered it an M6 star, where it basically fit into the luminosity and its mass, but they said that for a star it was kind of weird and very rare, because the star was so, like, some of the properties that they've discovered with it were just kind of unbalanced. You just don't see that in And it just goes to show you that, like, just like anything else in science and space, like, everything's judged differently. You know, you could find a star that maybe it's so big, but somehow it's like a dwarf star where, like, it doesn't burn as high, but maybe it's like really freaking large, like it burns, and its life cycle is a lot older, and therefore it maybe moves not as fast because of its bulkiness and size, because, you know, it's just a big giant sphere of plasma. I mean, there could be anything out there, and it would really take a bunch of scientists to really, like, examine every single one of the subgroupings of that galaxy or that star in particular and really be able to make sense. Like, if there's something they're really looking for, you just have to look at the numbers and try to judge it based on that. Because if you're learning that way, you will see, like, what stars harbor what based on their luminosity, their mass, their size, their spheres, the amount of material they give off, maybe even their life cycle. You know, another good example, their temperature, how hot do they burn, and what way are they possibly going to go as far as the cause and effect. Are they going to collapse into a black hole? Are they going to supernovae? Either way, that material is going to go somewhere, and it's going to either create something else or more stars. You know, more stars or more universes, and therefore energy multiplies either way. It's just, you know, what direction and how is it going to go about doing it. All right, and then we'll talk about irregular galaxies. Now, irregular galaxies are just as their name does imply. They're irregulars. There's not enough bar structure characteristics to be able to make sense of if they're ellipticals. It's basically, you know, ellipticals, bared ellipticals, or bared spiral galaxies, or spiral galaxies to begin with. They're basically just as their name implies. They're just kind of like a wild card, sort of. They basically are just their own shape, and we just basically call them, like, just, you know, kind of, it's just off to the side. So irregular galaxies are, just as their name implies, something completely different. They're still galaxies, but there's just such an unbalanced nature between them that, you know, they just don't look the way they should. You know, maybe they formed poorly, or maybe they still do what they do, but it's like, you know, there's a better chance that you're going to find, like, an unbalanced nature in between them, as far as kind of like going like to like what an elliptical galaxy was. Like, you know, like it's trying to form into like a spiral galaxy, but it ended up becoming something else. And then an irregular galaxy is just, you know, just that. It's like, it's kind of like an elliptical galaxy, but much more stranger than that. So you basically have, like, the same thing you'd find in a galaxy. You know, you have, like, your spiral arms, your halos, your disks, your black holes, your luminosity, your mass, your stars, your planets, your moons, your asteroids, you know, whatever, you know. But basically, though, you're going to find out that those galaxies might actually have certain things in them that you don't really find anywhere else too. So, but you never know. I mean, you know, what star system has somebody completely discovered? What galaxy out there have we really seen everything of? We haven't seen everything. So there's always that room of mystery somewhere, one way or another. All right, so now we're going to start getting into some subgroupings of, like, some of the galaxies. Now, there's what is known as a Lincular Galaxy. The galaxy itself mostly consists of, it's a combination in intermediary, where it's like in between, a subgrouping between spiral and elliptical. It may be in some cases irregular galaxy, but again, keep in mind though, this is like kind of like the same argument that, you know, some people were making when they once said that Pluto wasn't originally a planet, because, you know, and some people never understood that. They said, well, how is it that it could be a planet, but it's classified as a different type of planet? Because it's a subgrouping. Like, for example, like, and even nowadays, like, you have like Mercury that is considered even smaller than Pluto, would actually be considered a dwarf planet. So you have planets, yes, but it's a different size planet. And it's like the same thing with these subgroupings with galaxies. They're still technically spiral and elliptical galaxies and irregulars, but you're more or less close to give it like its own meaning of, like, you know, for even more complex and very in-depth classifications. For, like, so in all intents and purposes in this case, it would basically be like saying that the elliptical galaxies, or the Lincular galaxies, would actually be still classified in their own way, but it's just like they're kind of lacking behind when it comes to like more or less like what a spiral, an elliptical, and an irregular galaxy can do. It's basically like, and keep in mind, that's just like anything else in the universe. Everything is evolving somehow, whether it's slow or it's really fast or it's long term or it's just really short term. It really depends, but it goes to show you that just goes to show you that as a scientist, that's why they have so many classifications, and that's why I'd still say like being a scientist can be like one of the hardest jobs in the world and easiest, because you have to really first of all identify what you have, but it's also necessary to be able to organize things very complex and simplifications, because if you can do that, then you basically have what is known as an easy way out when it comes to being able to identify what you have. So like even somebody like an astronomer or a cosmologist who studies the universe, you know, you're gonna find a lot of stuff in the universe that might actually fit into something else, but it's okay to give it another term because it's performing in such a way that, you know, maybe not too many other galaxies are giving off. So that's why we have this classification of, it's kind of like a combination of other things. You got some elliptical procedures, and then you got some spiral galaxy. It's like the disk, you know, but it doesn't, you know, do so many spiral arms, but it's like, it makes up for it some other way. So it's a balance in between. It's kind of like, again, wild cards, but in a different way. It's also worth noting that like they use up some of the material that they have in a way, and therefore like they have what is known as a lot of old aging stars, but also at the end of the day, you know, some of these stars might not necessarily be performing like a pure spiral or a pure elliptical or a pure irregular galaxy, depending on how far out you want to go. So basically it's just it's like a very old galaxy that's just like that could live a very long time. But it's basically kind of like a brown dwarf star, like in the sense that it doesn't burn as hot, but it lives so long though, if you can kind of see what I'm getting at. So therefore it basically is a galaxy that its energy is there, its energy can't be destroyed, but because it has so much energy, depending on its size and its aging, it's probably going to be there for a long time before it completely burns out and it becomes something else, or eventually just collides with another galaxy. It could travel even further and possibly merge with something else. Kind of like how the Milky Way galaxy is merging with the Andromeda Galaxy, for example, or the Andromeda Galaxy is merging with the Milky Way galaxy. You know, it's actually very interesting how matter is kind of like a liquid. You know, like when two bubbles hit each other, they connect and they make a bigger bubble if they don't pop. Or like water, you know, once a liquid, something touches it, it just gets even bigger. You know, two puddles move together. So basically, there's also these other galaxies called peculiars, and there's two types of them. There's what is known as a capital AGN, which is like active something nuclei. I forget what the G stands, or the G stands for. And then there's what is known as like active galaxies. They basically are kind of like irregulars, but like a more subgrouping of irregular. They have like an unknown shape, composition, and size, basically. So basically, it's like they're basically like a bunch of stars and material all together that can do all sorts of crazy things. Okay, so the AGN stands for active galaxy nuclei, and the other one was called interacting galaxy or interactive. So basically they make up 5 to 10% of the known galaxies that we know of right now. Again, if it's still one or the two, it's still a peculiar galaxy, but basically they all just interact differently. It's literally as its name implies. It's peculiar because it's noteworthy, but at the same time it's kind of predictable too. Like, because again, you know, when you study galaxies, all galaxies have to have a certain thing in common: mass, luminosity, stars, planets, galaxies, certain stardust, radiation. There's so many different types of ones that you probably don't even find, and whether they're real galaxies or subgrouping galaxies, they'd still be real galaxies, but they'd just be like the most common ones you find. You'd be very surprised what a lot of people overlook in a lot of cases and what it can actually mean. So peculiar galaxies, They're not too rare. They still do, they're not that common either, but like, you know, but they're not like non-existent. It's like we do know about a lot of these galaxies. And there's probably a lot more out there that haven't been discovered. But basically, you know, they probably do have alien life in them some way, somehow. Just another way the stars are formed, rather. All right, so here we have what is known as a ring galaxy. It's mostly, as the name implies, it's got a big giant ring around it and a lot of stellar dark matter. But it also has what is known as like young blue stars. Keep in mind the blue is actually the hottest color that a star can burn. So that's actually very interesting, because when you really think about it, there have been scientists that have speculated before that there are certain stars that might not exist because we never found one. But depending on the galaxies that we discover and what they're classified as, could very well prove us wrong. Like, you know, like I think they're called Quasar stars or Quasar stars, something like that. But they're supposed to be like way bigger than a hypergiant star, and they also call them black hole stars. But they're so big, but we haven't found elements that support like that size. So it's possible that maybe we're just looking in the wrong galaxies. And it's kind of like the same thing with like a ring galaxy. You know, a lot of scientists say that, you know, you don't really find too many brightly young blue stars that are burning that hot, because that's actually kind of a bad sign for some galaxy stars, because if it's a blue star, it's going to burn so hot that it's probably going to use up so much material. Kind of like how our sun is actually white. If I remember correctly, white is like the second hottest color burning, and then it goes off to that. But I could be wrong though. So depending on how fast it burns and depending on how hot it is, also affects like everything else. Its lifespan and maybe what kind of star it's going to become, based on when that last moment hits, where it either blows up or collapses on itself. Or maybe it goes both ways. Who knows? But yeah, it's definitely strange, like some of the stuff we found in space. And this would actually be where you'd want to find a lot of blue young stars, is obviously in the ring type galaxies. Now, ring galaxies, let me look this up again because I don't remember. Now here's where it gets really kind of confusing. Hence the ring galaxy. Okay, so obviously it's a ring with certain material and dark matter that doesn't really look like it's there. They've stated, there have been scientists that have stated that there are galaxies that orbit other galaxies. This is where we kind of get a little confusing. This is where you start jumping into what is known as like virtual galaxies and super clusters, basically. Basically galaxies that are inside other galaxies when you zoom in to enhance, like a kind of like the star Stephenson 218. The 218 was actually supposed to be a there were like 18 other objects that were found in its area, like a colony of stars, basically. So basically galaxies kind of do the same thing, where something could have hit it. It might have formed its material in that section of the galaxy, but it could have been a part of it's now like its own galaxy that could have been a part of another galaxy. It's like a part of a galaxy that broke off and went and formed like another galaxy. It's as strange as it sounds, but it could happen though. I don't know really 100%, but how that really works. But at the same time though, it's possible that or maybe it's like kind of like a reverse effect, where it was another galaxy at one point, but then it slowly merged with another one, and then but like this is just like a small portion they're observing, so it's like maybe it's kind of like two galaxies in one, sort of, if that makes any sense. So they're observing like a ring galaxy within maybe another galaxy, but I don't think in this case the galaxy that we're looking at is actually referring to like another galaxy. It's just its own galaxy. But basically it wouldn't surprise me, because there have been more than one way a galaxy can form, and galaxies that there's been evidence that other galaxies have merged with other galaxies, so they can in fact collide with each other and maybe possibly break away. Although you have a better chance of being able to have a galaxy merge with one galaxy and just become a bigger galaxy, rather than it just breaking off and maybe forming another galaxy. Or maybe what happened was the ring galaxies eventually, they're basically very like young galaxies. They could have just formed recently, but still they're some of the younger galaxies compared to like some of the other stuff we know of, and hence its size, hence what it has, and it doesn't have that much mass and material, but yet it's got, ironically, some of the brightest stars that they've discovered that, well, probably might not have life on them, but due to their huge luminosity, because again, brightly burning blue stars, and you have yourself a whole lot of unanswered questions that, I mean, somebody has to find another ring galaxy to be able to make sense of all this stuff. So that sounds pretty interesting, actually. So basically, it talks about, it might actually prove to us how other galaxies can form and how they might be able to break away from each other, as well as how many galaxies could have formed to make, you know, like a supercluster or a super virtue galaxy, or however you pronounce it. Basically, other galaxies inside other galaxies, big colonies of galaxies. You have to take like a big telescope, zoom it in, and then kind of zoom into like different areas that might look like there's nothing there, but there could very well be just a little bit further out. Okay, so like right now we're just basically gonna start naming off like some other galaxies that I'll make videos about like right now, and kind of give a description based on what they are. And so basically you have like also what is known as like dark galaxies, for example, where its name is pretty obvious. There's not that much starlight, or they're all spaced out, and the luminosity is really dense. So like if you wanted to find like dwarf stars, the ones that don't burn as hot, they like burn coolly, the ones that could probably live for trillions of years or even longer than that, this is probably a good place you could find them. You also have like what is known as starburst galaxies, where they're basically like, depending on like the luminosity and like maybe even some of the supernovas that have happened over time, they're much more likely to happen based on the just how the stardust lights up with the nebulous material and the matter, and maybe some antimatter if it's there, but probably not as much, because the way our universe is constructed of mostly, unless there's like somehow another galaxy that goes from a black hole to here, somehow like another universe, then it would basically create a bunch of antimatter. But basically, you find a lot of strange galaxies where they have some of the strangest properties, and obviously a lot of unknown material, so you'd have to capture it first and be able to identify protons, neutrons, and electrons. But starburst galaxies really do have a lot of like solar flares, a lot of gamma ray radiation bursts, and some of them have created like different types of radiation that you can tell once you figure out what kind of radiation it is based on the electromagnetic fields, and you can figure out like where it fits into the ultraviolet lights, for example, or not just that, but the electromagnetic spectrum. You basically could tell like how radioactive something is just based on the material that it's giving off. In starburst galaxies, you see a lot of that, basically. You basically have what is known as blazer galaxies, which are basically like interactive. They have like they're active galaxies, basically. Now, again, another subgrouping galaxy. Basically, they have like what is known as different types of interactive jets that are kind of like radioactive material that like be pointed to the earth, kind of like an alien death ray, it seems like. You know, it's kind of strange, but it's like the way the universe likes to travel in its own way, and you have all these different galaxies that just kind of give off weird frequencies and radioactive electromagnetic pulses. But the way they do it, though, is why they get classified differently. Because like all these, if you really think about it, like every galaxy can have something you can find in it. That you can probably find everything in some galaxy. But like for example, you find a lot of stars in galaxies, but like they all implement something different. Hence the different classifications that they have. And then basically, then you have what is known as like a radio galaxy. Now, here's where it gets even stranger. I have stated before on this channel, but I'm sure there's some people that probably don't know it exists. There is a galaxy, and this really just goes to show you that there's a lot of outdated information on Google, Bing, everything, because there's just so much stuff that's being discovered, but it's like, you know, it doesn't get released in everybody, and it always makes the headline. So this stuff goes unnoticed by a lot of people. So you should always question how big something is in science. Now, if you were to type in like what is the biggest known galaxy that we have discovered, I'm going to tell you right now it's not IC1101 anymore. As a matter of fact, it's actually what was a galaxy that was like, it was like I'm trying to remember how you spell it. It's a capital J, there's a 0, a 4, 5, 25, it's like an underline, and then it's like 0, 5, 4, 3 or something like that. It's actually, some of the numbers are wrong, but it's, you'll get what I'm saying though when you find it though. But basically, there is a galaxy they discovered that it's a radio galaxy, it's a radioactive galaxy where, but again, every galaxy has like radioactivity in it, so it's basically just the, it's just a different type of illumination and all that. But this galaxy was at least, and I think it's even bigger than this, because again, based on like size comparisons and all that, but it's, they said it was like 17.4 million light years in diameter, at least. And it's it gives off quasars, which again you can find, again, radioactivity, illumination. So if there are a lot of stars, it's probably got a lot of mass. It's a big galaxy, so everything's all compacted, and the stars that you probably find there burn so brightly. So that's something to think about. You also have the possibility of galaxies that are so big that you could probably find like so many planets that are like, when flying out of their galaxy, they have like different types of elements, mass, radiation, all sorts of things. So it basically like a huge variety basically of like all sorts of crazy things you can find in it. It's like just this big galaxy that has been undiscovered and nobody really knows, like, it's lost history. It just goes to show you how much we don't know about it. But it's very dangerous and very beautiful in its own way. You also have what is known as liners. They're kind of like another active galaxy classification. Liners actually stands for something. It's like a low ionization measurement. There's some other terms too, but but we're gonna kind of speed this up a little bit. So basically, as far as some of the galaxies they've discovered, they basically have certain properties that they lack, but at the same time they keep going with. Basically, liner galaxies, to make a long story short, are dominated mostly on very, very low ionized elements. I don't know if I'm pronouncing that right, but again, that's how you spell it though. So basically, you have galaxies that perform certain things slowly, but at the same time though, they produce like such devastating results in some cases that it might actually be one of the most dangerous places to live if you were to somehow get caught in a galaxy like this. I still think radio galaxies are probably like the most dangerous, because there's just so much luminosity and there's so much radiation. And I mean, if that stuff doesn't kill you, then, I mean, unless of course the material, it's like the stuff that evolves in that galaxy is like forced to evolve to survive the electromagnetic fields and in the ultraviolet rays or the gamma ray bursts and the quasars and the black holes and the sun, the supernovas, and like it's crazy, like some of the stuff that, the universe is a wild place. It really just like, wow, incredible. Like, what else is out there? So then we also have what is known as Cypher Galaxies. It's like Seytert, or Seyfert, somewhere around. So like a Cipher Galaxy is basically one of the largest active galaxies that you can find. Again, they're kind of like another subgrouping, but you get the idea at this point. There's a lot of subgrouping. But it dominates certain properties of like radiation of quasars and radiation basically. So you're gonna find a lot of this stuff in this galaxy too, and there's other stuff too, but a lot of quasars, a lot of black holes possibly. Yes, a lot of radioactivity. I just looked this up. Radioactivity and a lot of highly luminous material. So if that's not enough to convince you that you probably are going to find some super big stars in there, they're either blue stars where they're burning so brightly, or they're just so big that the bigger the star is, it's either going to supernova. It kind of basically like a sort of another dangerous style galaxy you wouldn't want to be caught in the middle of if you were in the wrong star system to begin with. What else to think about? Yeah, so here's something else to think about. So like, based on some of the Cipher galaxies that we've actually discovered and observed, they, like, some of the core stars that they have seen actually outbeats, like, some of the core stars that they found as far as their luminosity goes is like that of like the whole Milky Way galaxy's illumination. Like, there are some galaxies that you couldn't even begin to imagine, like, how crazy, you know, that is. Like, so much electromagnetic radiation can be found in those galaxies. Again, like, kind of like radio galaxies, radioactive, to the point where it literally does speak its name. It is a very, very dangerous place. And while not necessarily a galaxy term, but more of like, well, not a galaxy itself, but like can technically be a galaxy, like if you really wanted to be. It's like more of like a term of radiation you find. But I wouldn't be surprised. I mean, they probably could find like a galaxy, call it a quasar galaxy. So let's just kind of entertain the idea. So like a quasar by definition is a very bright light that's given off based on radiation, and you basically can find a lot of quasars between like black holes. Like, you might remember, like, there was an article that was written a while ago where they stated that for like one of the first time ever we've actually seen light, you know, rotating from a black hole. So you could kind of see the black hole and the light particles, but basically the black hole hasn't sucked all that light up. That's why this was kind of a big deal to a lot of people, is because you could kind of see that, yes, there was something there. Because black holes, you can't really detect them, but you have something to see it based on the object in the middle, and that object would have sucked all that light up and eventually just would have dissipated everything around it, would have sent it somewhere else. So if that is true, then basically the light itself would have dissipated into, like, so basically you have quasar rings and whatnot. So basically, I wouldn't be surprised that you could say that there are galaxies out there that could be quasar material, just nothing but quasars. And there you go. So yeah, quasar galaxy, basically, if you want to go by that. But other than that, you find quasars in just about every other galaxy. I mean, hell, even our galaxy even has nothing but quasars here and there. And there could be solar systems out there right now that's creating a quasar effect right now based on its luminosity and maybe a supernova, for example. I don't know if that's saying the same thing, but basically, not to get confused with gamma ray bursts and solar flares, but that's just another type of radiation on an electromagnetic scale, though. All right, and here's another one. Luminous infrared galaxies. These ones are very interesting. These give off radioactive material that is great in luminosity, greater than 10 to the 11th power. So basically, like I've said before, if you look at the electromagnetic spectrum, you can actually examine the material that comes out of it, and you can see very well just what kind of gamma ray bursts or quasars or solar flares or basically even ultraviolet lights. But these are like some of the most powerful material on the electromagnetic scale. Again, 10 to the 11th power. With that being said, you find a lot of stuff like this flying around in a galaxy. This is stuff that can just burn things. It's like a plasma ray, like psh, you just destroy something. Pure energy. I kind of have a theory kind of right now. If there are other galaxies out there and other universes that exist in other dimensions, these probably would be one of the very first galaxies that could happen, because while the universe is still being created in the universe, like some of these galaxies, they burn so hot and they burn like so fast that they're creating so much energy that it's, you know, it has top like acceleration, it has top luminosity, it has basically just enough bright electromagnetic power to be able to do such a thing to the point where it doesn't slow down. And some of these galaxies could have been so big, so this would explain why like nuclear fusions and fissions on a level that we don't even understand. You know, nuclear fusions and fissions, if you don't know, basically are two terms that they use to explain ions creating other elements, like, or subatomic particles, repelling and attracting. Just kind of think about that. While they're sitting there burning so fast, creating so much friction in a core of a star, and it causes it to illuminate the way it does. does. Again, friction. Everything moves in space. Everything's moving to the point where, depending on how fast it burns, depending on how fast it orbits, everything is creating some kind of radiation. Even a true annihilation with antimatter and matter would only result in more radiation. So it is proof that the law of conservation and the first two laws of thermodynamics states that energy cannot be destroyed, but it can only be multiplied. And that would explain why everything in the universe is infinite, and I do believe that. I think that a lot of us underestimate what kind of galaxies are out there, what kind of material that we have yet to find, and there just never is no end to it. Even if we think that that material can't be discovered again, or it couldn't happen again, maybe it's happening somewhere else, because we don't see everything. So there could be another galaxy out there right now that could have created itself, and it basically could have been a super illuminated, without the term super in there, illuminated infrared galaxy. And it could have just been so big, even like those quasar stars we talked about before could have, or those quartz stars could have existed a lot. Those black hole stars could have existed because they would have had the material, the elements, the luminosity could exist. Or maybe they still do exist, but we're just looking in the wrong places. Because one, you need a big galaxy, a very big galaxy, and when you need the right material. But where do you find that at? And obviously you've got to keep looking in space. Eventually you're going to find things that you don't have on record, so you have discovered something new that nobody else knows about. So this would be a good example. They say these were much more common back when our universe was very young because it was burning, it was hot, and that is proof right there that there has to be more than one universe, because that material had to have come from somewhere else. And if that material came from another universe or a dimension, let's just say, or maybe just another point in the universe and it came here, because galaxies can still get hot as they burn really fast, that material would have been so, I'm trying to think what the word is, it would have been so active and so young that it could cause high ultraviolet light radiation, as well as infrared, and it could also cause a luminous material because it's burning hot, it's burning big, and it might have burned for a long time that even the size capacity of it wouldn't have made a difference. So these galaxies would have had stars and material that we probably wouldn't even have seen until now, and therefore it would have created even more stars, more energy, more renewable sources to give off as like that would kind of make something like a plutonium bomb look like a joke in comparison, you know, because like all this material, it's just supernovas and black holes and radioactivity basically, because radiation is heat basically. Oh yeah, and so basically they've also had this term where it's like what is known as like early galaxy formation, preservation. So basically, hence the name preservation. What's actually really interesting about this is they've actually discovered you could examine, it really just goes to show you like how different galaxies really are acting that's really right in front of our eyes that we don't see. Once you start taking like a galaxy, you look at it, and then you look at it again through like infrared technology or maybe some kind of other scaling of its light, you actually can see like so much more out there that's just not visible. And therefore you have different results, like different galaxies that have different properties that we don't see. There's so much happening. Basically, what they're trying to get at with this is that there's a lot more than what meets the eye. Again, more proof that everything is infinite, and there's more wild properties that can very well sustain a lot more possibilities that we don't even think of yet, that, you know, other elements, other galaxies, other universes, other life forms on other planets, more reasons to exist. It basically say that existence is basically what it is. Yeah, so I wouldn't be surprised in the slightest. Okay, so here's something else to think about. If there are so many galaxies out there right now, even galaxies that we don't see, is it possible we could go back in time and still be able to exist somehow? Like time travel. Would time travel work the way we think it is? And would it be able to produce even more results that we don't see? And I think so, without actually changing everything, kind of like how, but I guess we'd have to understand, you know, how do we go into another dimension without that still exists on the same timeline? Kind of like how, if anybody remembers, like in Back to the Future, he was trying to explain to, you know, how Christopher Lloyd was trying to explain to, you know, what was his name, Marty McFly. He, you know, the Doc was trying to explain to Marty McFly, trying to explain to him like how they had to go back in time, but like to a universe that still existed on the same plan. They wish to change it onto a parallel universe on a different time period in the same existence. So it's actually very interesting to think that how could we really tell such a thing exists? How could we really differentiate the difference between the past and just a parallel universe? Very interesting. And so you also have like another type of galaxy. Now, once again, you can find these in galaxies too. It's not just a galaxy. Kind of like how, like, if there is such thing as a quasar, galaxy, there would also be like something like a halo galaxy. You know, again, just goes to show you that there's probably an infinite number of possibilities we haven't even thought of yet. But anyways, so if there is such thing as a halo galaxy, you would basically have a bunch of galaxies that consists of the halos. You know, so basically you would take like the halo of a galaxy and it basically extends like its outer reaches into its main component, and then it would actually end up becoming like what it is. Is it like a spherical, like galactic halo, or is it like a galaxy that could have like stuff that overlaps itself? You have also a lot of visibility with again, quasars and more radiation, but it's just interesting to think that like somewhere in that galaxy that we could very well have a lot of material that could just be flying around out there, and it's getting stuck in between like other galaxies, and so it causes them to evolve in a way. So every galaxy's moving fast and it's evolving, and you basically could say you have like what is known as like a galactic evolution, or like kind of like planetary evolution. You know, all material is changing, and it's always creating some kind of property evolution, progress rather. So basically the universe is alive and well, basically. And this just kind of gives you an idea of how many different ways we have thought of over the years. There's probably many more, no doubt, but there's always an opportunity everywhere. So I will find more information on this stuff and make more videos about it if I can. But as of right now, this should be good enough. So yeah, if you like these kind of videos, subscribe. If you want to see more, let me know. And if you want to support my Patreon, the link's in the description. You don't have to, but it would help out a lot. And I'll see you all in the next episode.